Welcome back to another episode of AI Talks with Chris and Nita. We're diving deep into something pretty amazing today. It's called backpropagation. You know how we learn from our mistakes? Well, backpropagation is how AI does the same thing, constantly getting better and better at predicting stuff.
Yeah.
It's kind of like giving machines a brain that learns.
Yeah, that's a great way to put it. It's really like the engine behind a lot of the AI we're seeing pop up everywhere these days.
Right, exactly. But to really get into it, we need to start with the basics. Neural networks, I know they're kind of modeled after the human brain, but can you break it down for me? What are they actually?
Okay, so imagine a network. It's super complex, lots of interconnected nodes, kind of like a web,
Web, yeah.
Each of those nodes, we call it a neuron. It's a little computational unit, and it's processing information. And all these neurons, they're working together, like passing information back and forth to analyze the data and then make predictions.
Okay, I think I get that. So is it like a team working together?
Yeah.
Like each neuron is kind of doing its part to get to the final outcome.
Yeah, exactly. Think of it as a relay race. You've got the data, it's like the baton, right? And it's passed from neuron to neuron.
Okay.
Each one processes it a bit and passes it on. But here's the thing. Each neuron has a specific job. We call it an activation function. And that determines how much it responds to the information it's getting.
Oh, so it's not just a simple pass off.
Wow.
Each neuron has a personality, you could say, right?
Yeah.
It decides how much it wants to be involved in the race.
Exactly. Some are really fired up. Others are more laid back.
So how does this network actually learn, though? Where does this backpropagation come in?
So backpropagation, that's the coach in this relay race. It's a training process that really makes the network better. Let's say the network makes a prediction. It's trying to identify a picture. Say it's a cat, but it guesses dog.
Oops.
Right. So backpropagation kicks in and it looks at that error. How far off was the prediction? And it figures out which neurons were most responsible for that mistake.
So it's like reviewing the game tape after a loss, figuring out what went wrong, right?
Exactly. But instead of yelling at the players, backpropagation adjusts what we call weights and biases. Think of those as dials that control how much each neuron's output affects the next one in line.
Interesting. So it's tweaking those connections, the connections between neurons, based on the errors it made.
Exactly. It makes some stronger, some weaker, so the next time the network sees similar data, it's more likely to get it right.
Okay, I think I'm starting to see it now. The network makes a guess, backpropagation checks how wrong it was, and then it goes back and adjusts all those little connections to make it better for next time. So it's like a continuous learning process.
You got it. And that process, as you said, it keeps going, making predictions, getting feedback through backpropagation, refining those connections, always improving.
That's pretty incredible when you think about it. It's like machines actually learning from mistakes and getting better over time.
It is. It's the basis for so much of what we think of as intelligent in machines today. But to really see the power of backpropagation, we need to look at how this whole feedback loop really works. And that means understanding two key stages: the forward pass and the backward pass.
Okay, I'm all ears. Let's break down those two stages, starting with the forward pass. What exactly happens there?
So the forward pass, that's where the action starts. Think of it like the first run in our relay race. You've got the input data, whatever it is, a picture, a bit of text, and it's fed into the network. And then it flows through each layer, neuron to neuron, just like that baton being passed. Each neuron processes the data a bit, applies its little activation function, and then passes its output to the next layer.
So the data is kind of cascading through the network, each neuron adding its little bit to the puzzle.
Exactly. And it goes like that until it hits the final layer, which spits out the network's output, its prediction.
Got it. So the forward pass is all about getting from input to output, making that first prediction. But what happens then? That's where the backward pass comes in, right?
You got it. The backward pass is where the real learning magic happens. It's like that after race analysis, the coach is reviewing the performance and figuring out how to improve for next time. And in our case, the coach is the backpropagation algorithm.
All right, let's dive into that backward pass.
Okay, so let's imagine our network is trying to identify a picture. Let's say it's a picture of a cat. It goes through the forward pass, analyzes the image, and then confidently predicts, a dog.
Whoops. Not quite.
Right, not quite. So that's when that backward pass kicks in. The first step is calculating the error. How far off was that prediction from the real answer, the cat?
This is like figuring out how wrong it was.
Exactly, yeah. And then here's where things get really interesting. The network doesn't just say, like, okay, my bad. It needs to figure out why it was wrong, which neurons kind of mess things up.
But how does it do that? It's not like you can talk to each neuron and be like, hey, what were you thinking?
Well, not exactly. This is where we need to talk about gradients. Imagine you're standing on a hillside. Okay. A gradient basically tells you which way is the steepest climb uphill.
Okay, so it's kind of like a signpost pointing uphill.
Yeah, exactly. But in our case, uphill, that represents more error. We actually want to go downhill, towards less error. So the network, what it does is it calculates the gradient of the error in relation to each neuron's weights and biases.
So the gradient, it's basically telling us which way to turn those little dials, the ones that control the connections, right?
You got it. The bigger the gradient, the more that weight or bias contributed to that error. So the network makes these little adjustments to each one, like nudging them in the opposite direction of the gradient, sort of taking a tiny step downhill towards a smaller error.
So it's kind of like that game, hotter or colder. Like the network is adjusting those settings based on how wrong it was.
That's actually a really good analogy. And just like in that game, the steps, they get smaller as we get closer to the right answer, allowing for finer and finer adjustments as the network gets better. And this whole process, it's repeated over and over for each training example, gradually fine-tuning those settings until it's making accurate predictions.
Man, that's so intricate. It's amazing how something as complex as learning can be broken down into those mathematical steps. But I'm curious, why go through all that? Why not just, program the network with all the right answers from the get-go? Wouldn't that just be easier?
That's a great question. And it actually gets to the heart of why machine learning is so powerful. See, in a lot of real-world problems, we don't actually know all the right answers beforehand. Or it would be impossible to try and code them all. Take image recognition, for instance.
Right, because there's so many ways a cat can look.
Exactly. We can't possibly program the network with every single image of a cat that exists. We need the network to be able to learn from data, to adapt, and be able to handle new situations that we haven't specifically programmed it for.
So backpropagation is kind of letting the network figure out the patterns in the data on its own, right? Without us having to spill everything out for it.
Precisely. It's what lets machines tackle these really complex real-world tasks where things are constantly changing or maybe just too complicated for us to define exactly how they work.
Okay, this is starting to make sense now. So we've got this system of neurons all connected. Then the forward pass where the data flows through, and then this backward pass where it looks at its mistakes, calculates those gradients, and then adjusts those connections to get better. It's like giving machines the ability to learn from experience, just like we do.
Yeah, that's a great way to put it. And the best part is, the whole process, it's automatic. We don't have to go in and adjust each weight and bias by hand. Backpropagation takes all the work, constantly refining those settings so that the network keeps getting better at making predictions.
This has been a really fascinating deep dive so far. I'm starting to really see why this backpropagation thing is such a big deal in AI.
And while backpropagation isn't perfect, understanding it really helps us appreciate all those AI advancements we see popping up everywhere, from self-driving cars to personalized medicine and so much more.
You're absolutely right. And for our listener, I think the takeaway here is that even though we're talking about complex math and stuff, the idea behind backpropagation is actually pretty simple, right? Learn from your mistakes, adjust, and get better.
Couldn't have said it better myself. It's a good principle for anyone, really.
Absolutely. So to our listener, we encourage you to keep that curiosity alive, never stop learning, and keep exploring this amazing world of AI. Who knows, maybe you'll be the one to come up with the next big breakthrough.
That's a great thought. Thanks for joining us on this deep dive into backpropagation.